This chapter discusses legacy databases. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Balsens and I'm one of the authors of the book. Although legacy databases are obviously outdated and semantically inferior to modern-day database technologies, the reasons for reviewing them are threefold. First, many firms still struggle with legacy databases due to historical implementations and limited IT budgets. Hence, knowing the basic characteristics thereof is essential to the maintenance of the corresponding database applications and the potential migration to modern DBMSs. Second, understanding the basics of these legacy models will contribute to better understanding the semantical richness of newer database technologies. Finally, the concept of procedural DML and navigational access originally introduced by these legacy models has also been adopted by more recent databases such as OODBMSs. In this chapter, we cover both the hierarchical and Codasyl data model. Throughout the discussion, we extensively discuss the expressive power and limitations of both models. The hierarchical model is one of the first data models developed. The model originated during the Apollo moon missions program conducted by NASA. To manage the huge amounts of data collected, IBM developed the Information Management System, or IMS DBMS. There is no formal description available, and it has lots of structural limitations, as we discuss in what follows. Therefore, it is considered legacy. The two key building blocks of the hierarchical model are record types and relationship types. A record type is a set of records describing similar entities. Think about a product record type or a supplier record type. A record type has 0, 1, or more records. It consists of fields or data items. A product record type has a field product number, a field product name, a field product color, etc. A relationship type connects two record types. It models the relationships between record types. Only hierarchical structures are allowed, or in other words, only one-to-n relationship types can be modeled. Hence, a parent record can have multiple child records according to the same relationship type, but a child record has at most one parent record. A record type can be a parent in multiple parent-child relationship types, but it can participate in at most one relationship type as a child. Relationship types can be nested. In other words, a child record type can be parent in another parent-child relationship type, which allows to build hierarchical structures. The root record type is the record type which sits at the top of the hierarchy, whereas a leaf record type sits at the bottom of the hierarchy. Here you can see an example of a parent-child relationship type. A parent record can be connected to minimal 0 and maximal n child records. A child record can be connected to minimum 1 and maximum 1 parent. Hence, a child record is always connected to exactly one parent. No other cardinalities are supported in the hierarchical model, which makes it very restrictive in terms of expressive power. Remember that the relationship type is always summarized in terms of its maximum cardinalities. In our case, we can say that the hierarchical model supports only 1-to-n relationship types. This figure shows an example of a simple hierarchical model. We have three record types: department, employee, and project. The department record type has three data fields: department number, department name, and department location. The department record type participates in two parent-child relationship types. A department can have 0 to n employees. An employee is always connected to one department. A department can work on 0 to n projects. A project is always worked on by exactly one department. This is a very simple hierarchical structure. Department is the root record type, and both employee and project are the leaf record types. In the hierarchical model, all record data needs to be retrieved by navigating down from the root node of the hierarchical structure. In other words, the DML adopted is procedural, which is not efficient. The hierarchical model is also very rigid and limited in expressive power, since it allows only 1 to n relationship types. There is no support to model n to m or 1 to 1 relationship types. Hence, these must be implemented using workarounds. To implement an n to m relationship type, we can assign one record type as the parent and the other as the child record type. In other words, we transform the network structure into a tree structure, which will obviously involve a loss of semantics. Any relationship type attributes, such as the number of hours an employee worked on a project, will be put in the child record type. This solution creates redundancy, which is dependent upon both the amount of data in the child record type and the value of the maximum cardinality of the child to parent role in the original n to m relationship type. Let's illustrate this with an example. Say we have an n to m relationship type between project and employee. Put differently, an employee can work on 0 to n projects, whereas a project can be worked upon by 0 to m employees. To implement this in the hierarchical model, we need to map it to a 1 to n relationship type, which is obviously not ideal. Hence, we can opt to make project the parent and employee the child record type. This figure shows some example records for this implementation. Project number 10 has 3 employees working on it: employee 110, employee 120, and employee 145. You can also see that employee 110 works on all 3 projects: project 10, 15, and 20. Hence, the data of employee 110 is replicated for each project he or she works on, which is inefficient from both a storage and maintenance perspective. If the data of employee 110 is updated in one relation, it must also be updated in the other relations, or inconsistent data will occur. Note that the number of hours an employee worked on a project can be put in the child record type. Another alternative to implement an n-to-m relationship type is to create 2 hierarchical structures and connect them using a virtual child record type and a virtual parent-child relationship type. Pointers can then be used to navigate between both structures. The relationship type attributes can be put in the virtual child record type. This solution has no more redundancy, since multiple virtual children can refer to one parent. This figure illustrates our earlier n-to-m relationship type between employee and project, but now implemented using virtual child and virtual parent record types. The virtual children have pointers to virtual parents. Although this solution has no more redundancy, it is rather artificial and difficult to maintain. One-to-one relationship types are a special case of a one-to-n relationship type with n equal to 1. This cardinality cannot be enforced as such in the hierarchical model. Hence, the application program should take care of this, which is not efficient because we are now forced to include part of the data definitions in our applications, which hampers maintenance and consistency. The hierarchical model only allows relationships of degree 2, or in other words, with 2 participating record types. Recursive or unary relationship types with degree 1, or relationship types with more than 2 record types, need to be implemented using virtual child record types. Finally, the maximum and minimum cardinality from child to parent is 1. A child can thus not be disconnected from its parent. This implies that once a parent record is removed, then all connected child records are also removed, creating an on-delete cascade effect. This figure shows an example of a hierarchical data model for an HR administration business process. It includes 2 hierarchical structures which are connected. Department is the root record type of the first hierarchy and employee of the second hierarchy. A department can work on 0 to n projects. A project is being worked on by exactly one department. The works on record type is a virtual child to implement the n-to-m relationship type between project and employee. It also includes the hours worked data item, which represents the number of hours an employee spent working on a project. The manager virtual child record type refers to the employee record type. Note that according to this implementation, a department can have more than one manager, since a department parent record can be connected to between 0 and n manager child records. The works at virtual child models the relationship between department and employee. 0 to n employees can work in a department. The manager's virtual child models a recursive relationship type which specifies the supervision relationships amongst employees. An employee can manage 0 to n other employees. The hierarchical model is not user-friendly and hard to interpret. It also has various model limitations. More specifically, our model does not guarantee that each department has exactly one manager. According to our model, a department can have 0 managers, or even more than one manager. We can also not enforce that a department has at least one employee, since it's possible that a department parent record has 0 works at child records. Hence, according to our model, it is possible that a department has 0 employees. Most of these constraints or rules have to be directly embedded in the application programs, which is not optimal. The Codasyl model is a next data model developed by the database task group of the Conference on Data System Languages in 1969, so not that much later than the hierarchical model. It has various popular software implementations, such as OODBMS from Culinet Software, which was later acquired by Computer Associates and rebranded into CA-IDMS. It is an implementation of the network model, which originally included record types and links and supported one-to-one, one-to-n, and n-to-m relationship types. However, the Codasyl model only includes record types, set types, and one-to-n relationship types. Although this may sound familiar to the hierarchical model at first sight, there are some clear differences as we will illustrate. Similar to the hierarchical model, the Codasyl model is considered to be legacy and has lots of structural limitations as we discuss in what follows. Just as in the hierarchical model, a record type is a set of records describing similar entities. It has 0, 1, or more records or record occurrences. It consists of various data items. As an example, a supplier record type can have data items such as supplier number, supplier name, etc. The Codasyl model provides support for both vectors and repeated groups. A vector is a multi-valued attribute type. In other words, an atomic data item for which a record can have multiple values. For example, if a supplier can have multiple email addresses, then this can be modeled using a vector. A repeated group is a composite data item for which a record can have multiple values or a composite multi-valued attribute type. For example, if a supplier can have multiple addresses, each with their street name, number, zip code, city, and country, then this can be modeled using a repeated group. The support for vectors in repeated groups is already a first difference with the hierarchical model. A set type models a one-to-n relationship type between an owner record type and a member record type. A set type has a set occurrence for each record occurrence of the owner record type together with all member records. Hence, a set occurrence has one owner record and 0, 1, or more member records. It is important to note that the Codasyl interpretation of a set does not completely correspond to the concept of a set as we know it in mathematics. Remember, in mathematics, a set is defined as a collection with similar elements and without ordering. However, a Codasyl set has both owner and member records, and it is also possible to order the member records. This figure shows a Codasyl set type with the corresponding cardinalities. An owner record can be connected to minimum 0 and maximum n member records. A member record can be connected to minimum 0 and maximum 1 owner records. Hence, a member record can exist without being connected to an owner record or can be disconnected from its owner. This is a key difference with the hierarchical model. A record type can be a member record type in multiple set types, which allows the creation of network structures. In the hierarchical model, a child record type can only be connected to one parent record type. Finally, multiple set types may be defined between the same record types, which is another difference with the hierarchical model. Codasyl data models are usually represented using a network or Bachmann diagram. Charles Bachmann was one of the important contributors of the Codasyl model. Here you can see an example. We have three record types: department, employee, and project. A department has 0 to n employees. An employee works in minimum 0, maximum 1 department. A department can work on 0 to n projects. A project is assigned to minimum 0, maximum 1 department. As with the hierarchical model, one-to-one relationship types must be enforced or modeled in the application programs, which should enforce that an owner record can only be connected to at most one member record. As with the hierarchical model, The addition of these semantic constraints to the application programs is not desirable from a maintenance perspective. N-to-M relationship types need to be also modeled using a workaround. As an example, consider the N-to-M relationship type between employee and project. Remember, an employee can work on 0 to M projects, whereas a project can be allocated to 0 or N employees. A member record, such as a project, can only belong to one set occurrence of a specific set type. Hence, we cannot just define a set type between the corresponding record types, for example, employee and project. One option is to introduce a dummy record type, which is included as a member record type in two set types, having as owners the record types of the original N-to-M relationship type. This dummy record type can then also contain the attributes of the relationship type, if any. The figure illustrates how the N-to-M relationship type between employee and project can be modeled in Codasyl by introducing a dummy record type, works on, which also includes the attribute type of the relationship, hours worked, representing the number of hours an employee worked on a project. This figure illustrates how this works with some example records. You can see that employee 120 only works on project 10, whereas employee 150 works on projects 15 and 20. You can also see that project 15 is allocated to employees 110 and 150. This implementation of N-to-M relationship types has serious implications for data usage. Suppose we have a query which asks for all projects an employee is working on. To solve this query, we first need to select a set in the set type between employee and works on. For each member record, we then need to determine the owner record in the set type between project and works on. If another query asks for all employees working on a particular project, then we need to navigate the other way around. Again, this is an example of procedural DML, since we must explicitly work out a procedure to solve our query by working with one record at a time. As we already mentioned, Codasyl allows to logically order the member records of a set. An example ordering could be alphabetically or based upon birth date. This can be useful for data manipulation. For the root member record type, the system can act as the owner, which is then called a singular or system-owned set type with only one set occurrence. Codasyl provides no support for recursive set types with only one participating record type. A dummy record type needs to be introduced, which is then defined as a member in two set types, each having as owner the record type of the recursive relationship. Note, this again implies extensive navigation when manipulating the data. Additionally, no set types with more than two participating record types are supported. This figure shows the Codasyl implementation of our HR administration example. The works on dummy record type models the N-to-M relationship type between employee and project. The hierarchy dummy record type implements a recursive relationship type modeling the supervision relationships between employees. The set type supervises models which colleagues an employee supervises. The set type supervised by represents the supervisor of an employee. Two set types are defined between employee and department. The works in set type models which employee works in what department. The manager set type models which employee manages what department. Finally, the set type in charge of between department and project models which projects a department works on. Here you can see our Codasyl model, but now with the cardinalities added as we would like them to be in the ideal case. Note that the underlined cardinalities are cardinalities which cannot be enforced by Codasyl. Hence, these cardinalities will have to be enforced by the application programs, which is not nice from a maintenance and efficiency perspective. The Codasyl model has various model limitations. For example, it is perfectly possible, according to our Codasyl model, that an employee can be managed by multiple employees. We can also not guarantee that a department must have exactly one manager. Finally, we cannot guarantee that a department has minimal one employee. We hereby conclude this chapter on legacy databases. We discussed both the hierarchical model and the Codasyl model. We illustrated both models and extensively commented on the shortcomings. This chapter is based upon our book, Principles of Database Management. For more information, I'm happy to refer to the website at the bottom of my slide.